A hydrogen atom contains a single positively charged proton and a single negatively charged electron bound to the proton by the Coulomb force. The Hamiltonian of the hydrogen atom can be expressed with either Cartesian coordinate or spherical coordinate, in which the Laplace operator in spherical coordinates is used. Hydrogen atom has a spherically symmetric potential, given by Coulomb's law. Thus, the spherical coordinates are more convenient for hydrogen atom. The stationary states of the spatial motion of an electron and an atom are called the atomic orbitals. Since hydrogen atom lives in three-dimensional space, there are three quantum numbers corresponding to an orbital. The principal quantum number, n, describes the energy level. They can take only positive integer values. The energy of an orbital is given by the same equation as the Bohr model. The sets of orbitals with the same principal quantum number value are referred to as an electron shell. The shells are labeled alphabetically with the letters used in X-ray notation. For example, the shell with n equals 1 is the K shell. The shell with n equals 2 is the L shell. The shell with n equals 3 is the M shell, etc. The azimuthal quantum number, L, is a quantum number for an orbital that determines its orbital angular momentum, L. Pay attention to the fact that this relation is different from Bohr's model. For a given value of the principal quantum number, n, the azimuthal quantum number is always an integer from 0 to n-1. The sets of orbitals with the same principal quantum number value and azimuthal quantum number value are referred to as a subshell. The azimuthal quantum numbers are labeled with the letters used in spectroscopic notation. The letters S, P, D, and F, for the values of L equals 0, 1, 2 and 3, were chosen to be the first letters of properties of the spectral series observed in alkali metals. Other letters for subsequent values of L were assigned in alphabetical order, omitting the letter J. Therefore, the K shell only possesses an S subshell. The L shell possesses S and P subshells. The M shell possesses S, P, and D subshells. The N shell possesses S, P, D and F subshells, and so on. The magnetic quantum number distinguishes the orbitals available within a subshell. It refers to the projection of the angular momentum in an arbitrarily chosen direction, conventionally called the z-direction. The magnetic quantum number takes integer values in the range from -L to L. In this illustration, the sphere represents the magnitude of orbital angular momentum for D subshell. The cones and plane represent possible orientations of the angular momentum vector for ML equals -2, -1, 0, 1 and 2. Since the revolving of charged particle creates a magnetic dipole moment, the magnetic quantum number affects the electron's energy if it is in a magnetic field, hence the name magnetic quantum number. This table summarizes the hydrogen atom orbitals for the first four levels. A subshell can be labeled with its principal quantum number followed by the spectroscopic notation of the azimuthal quantum number. For example, the subshell with n equals 1 and L equals 0 is 1s subshell. The subshell with n equals 2 and L equals 1 is 2p subshell, etc. Note that the number of orbitals in a subshell is 2L plus 1. For example, the S, P, D, and F subshells contain 1, 3, 5, and 7 orbitals each. The number of orbitals in a shell is n squared. For example, the K, L, M, and N shells contain 1, 4, 9, and 16 orbitals each. Thus, the ground level, K shell, is non-degenerate. The first excited level, L shell, has 4 degenerate states, that is, its degeneracy is 4, etc. Since each orbital corresponds to 3 quantum numbers, it can be labeled with the Ket notation. The ground state of hydrogen atom is the 1, 0, 0 orbital, also known as the 1s orbital. Its wave function is independent of direction. In other words, it is spherically symmetric. The radial function decays exponentially with the distance from the proton. As a result, the probability density of finding the electron also decays exponentially with the distance from the proton. The typical radius of the 1s orbital of hydrogen atom is Bohr radius, the same as the ground state orbital radius in Bohr's model. The first excited level, L shell, has two subshells. The s subshell has one orbital, the 2, 0, 0 orbital, also known as the 2s orbital. It is spherically symmetric and has a spherical node, where the probability density to find the electron is 0. The wave function has opposite signs at the two sides of the node. The 3, 0, 0 orbital is also known as the 3s orbital. It is spherically symmetric and has two spherical nodes. In general, all s orbitals are spherically symmetric, have n1 spherical nodes, and have different signs at the two sides of each node. The 2p subshell has three orbitals which are degenerate with the 2s orbital. One of them, the 2, 1, 0 orbital, is also known as the 2pz orbital. It has the form of two ellipsoids with a point of tangency at the nucleus. The two-lobe shape is sometimes referred to as a dumbbell, since there are two lobes pointing in opposite directions from each other. It is cylindrically symmetric with respect to the z-axis, hence the name 2pz. It also has a node at the xy plane, known as the nodal plane. The wave function has opposite signs at the two sides of the node. The 2, 1, -1 and 2, 1, 1 orbitals have complex wave functions. In chemistry, they are combined to form real orbitals for convenience. One combination yields 2px orbital, which has the same shape as the 2pz orbital but oriented perpendicular to it. It is cylindrically symmetric with respect to the x-axis, hence the name 2px, and has a nodal plane at the yz plane. Another combination yields 2py orbital, which has the same shape as the 2pz and 2px orbitals but oriented perpendicular to both of them. It is cylindrically symmetric with respect to the y-axis, hence the name 2py, and has a nodal plane at the zx plane. The 3d subshell has 5 orbitals which are degenerate with the 3s and 3p orbitals. The 3, 2, 0 orbital is also known as the 3dz square orbital. It consists of three regions of high probability density, a torus and two pear-shaped regions placed symmetrically with respect to the z-axis. It also has two nodes in the shape of a double cone centered at the origin. Other 3D orbitals have complex wave functions and are combined to form real orbitals like the 2p orbitals. The shapes of the combinations are the same. Each of them has four pear-shaped lobes. In 3D xy orbital, the axes of the lobes lie in the xy plane and has nodes at yz and zx planes. The 3dyz and 3dzx orbitals are oriented perpendicular to the 3dxy orbital and each other. The 3dx square minus y square orbital has the axis along the x and y axes themselves. There are 7 4f orbitals, each with shapes more complex than those of the d orbitals. The atomic orbitals of hydrogen-like atoms are used to approximate multi-electron atoms and molecules.